pleasure to introduce Rahul Mazumder, who has just come from MIT, and he'll be talking today about statistics with discrete optimization.
Yeah, thanks, Pauline, for the introduction. Thanks for all of you for being here, and thanks for the invitation. So I'll be talking about some computational mathematical programming approaches towards tackling non-convex problems, which is central in classical multivariate statistics or statistical learning. So the story goes as follows: that there are, most of the fundamental problems out there in statistics are inherently discrete, and there has been a lot of work in trying to understand different computational approaches towards these problems, and this has been this has been pretty much formed a significant interest in the community over the past several years. Now, in that context, towards computational understanding of these problems, significant emphasis has been placed on using continuous optimization methods, especially based on convex optimization. And they have had a significant impact towards our understanding of computational and methodological statistics. However, since I interact a lot with people in operations, research, and optimization, there are several other techniques, computational techniques out there, mainly in mathematical optimization, which unfortunately have not been explored to the fullest extent. All right, so that's essentially going to be the thrust of my talk over today. And largely speaking, the focus of our research, or the research of me and my group, has been can we use these techniques to better understand structured statistics problems? And there is often an interplay. So for example, as I'll illustrate today, when we talk about doing best subset selection for large-scale problems, we can start doing experiments with these for instances, for various regimes, and then as a part of the experimentation, the different insights come up, and then we need to be able to develop new methods in order to address. Okay. So sparse learning with discrete optimization. Here are some of the basic problems that I've been working on over the past several years. One of the core problems is in robust regression. Pauline has done some work on this. But when I talk about this robust regression over here, this is a non-convex variant, the way in which it was introduced way back in the days, in 1983, by Rousseau. The least median of squares regression, as well as its variant, its close cousin, as I like to call it, the least trim squares regression. There is, of course, the canonical problem, best subset selection, which has formed pretty much, which has been of great interest to the community over the past several years, or various relaxations of this. And of course, if you start talking about subset selection, there are various aspects of subset selection, or various esoteric versions of subset selection that we can talk about. One of them pertains to group structures. If you talk about group structures, then you can also talk about hierarchical grouping structures. So these are instances where the groups form a natural hierarchy. One classical example where these are used are in the context of hierarchical modeling with interactions. If you want to introduce sparsity, and if you want to get the interaction effect between variables 1 and 2, then ideally you want the marginal effects to be there as well. Okay, so this is one prototypical version of hierarchical models. There are again these other classic versions of L0 type problems. These arise in the context of piecewise linear models. So the left-hand side is an image which has 3 levels. The background level, there is a level over here, and then there is the other level. And given a noisy instance, I want to be able to reconstruct this image. The image on the right is an example taken from a classic textbook application of segmented regression. So these are piecewise linear models. Given a bunch of data points, I want to fit piecewise hyperplanes to it. How will I do this? Okay, so all these structures that I mentioned are screaming of discrete structures. And it turns out that if we tap into the literature of mathematical optimization, then there are techniques that we can use over there and port them to better understand these problems. there is another case of discrete optimization in the context of statistical models, and that is the classical low-rank factor analysis model introduced around in 1900s by Spearman. So over here, the discreteness arises from the low-rank structure. So some of the work that we did in this context, we do not do any relaxations, though I'm a big fan of nuclear non-relaxation. We don't do any relaxations. We start with the low-rank matrix factor analysis problem, and there is a very specialized structure in this problem. So what is this problem? I have a covariance matrix, and I want to decompose it into the sum of two parts. One of them is going to be a low-rank positive semi-definite matrix, and the other part, the residual part, is going to be a diagonal matrix, okay, with non-negative entries. So there is a lot of structure that we can exploit over there to think about approaching these problems. And then the recent problem that we have been working on, this is ongoing work, the notion of Gaussian mixers. If I have time towards that, by the way, how long is it?
An hour.
Okay, thanks. So I have time towards the end. This is a case where I'll discuss the basic problem of Gaussian mixers, and then I'll say though we like to use the maximum likelihood framework. If you think about developing tractable, in the sense of tractable optimization techniques, by tractable I mean methods in integer programming can be applied. We cannot really do a maximum likelihood estimation. We need to rethink the data fidelity criteria to be able to approach this problem. Okay, so I canceled this out because there are lots of problems over here. In order to, the focus over here is not to develop new methods in discrete optimization as such. The focus is to better understand these problems. And in the process, what happens is if you use an approach which only relies on mixed integer optimization, for example, there is one sub-branch of optimization, then you'll not be able to gain sufficient mileage. So it is important that we use different techniques in optimization, and by that I mean techniques in convex optimization, techniques in nonlinear optimization, as well as techniques in discrete optimization, and use them to solve the problems. Okay, so for the rest of the talk, or the majority of the talk, I'll talk about different aspects of subset selection. I'll start with an approach that we started. Many of you have probably seen that initial approach where we started using integer programming to solve this problem, approach this problem. And then, in the process of investigating this problem, it turns out that there were several questions that we came across, and while investigating them, we started embarking on new research directions, and I'll focus on some of them. Okay, so just to make sure that we focus on one particular problem. So this is the prototypical problem we'll be dealing with: linear regression, y equals to x beta plus error. Y is the response, x is a model matrix, and we desire interpretable or parsimonious models with good prediction and variable selection properties, which broadly defined. And we'd like to explore both statistics as well as computational aspects of it. The focus over here is not going to be on theoretical statistical properties. There has been a lot of work in this area already. But the thrust is going to be on understanding the statistical aspects of this by developing and using new computational techniques. Again, as you all know, there are several applications of this, so I don't have to talk about the application. So let's directly talk about the problem. So the sparse model with good data fidelity. The state of the art not too long ago that I'll go over is we want to solve the subset selection problem, and we all know, thanks to the research that has been done over here on very nice textbooks, documentation of these are available as well. It has excellent statistical properties in terms of prediction error, variable selection accuracy, and conventional wisdom has been that this problem is difficult. For example, if you use the R package heaps, then it cannot scale to problem sizes larger than n and p equals to 31. All right? So not surprisingly, you're told to stay away from this problem. Forget about solving this problem. This is a very difficult problem to solve. So to an extent, much of the statistical properties of this has been under mystery, mainly because we cannot play around with different instances of this and see how it works on data. So in this context, lasso or L1 regularization has been used as an extremely effective proxy. In terms of computation, this convex, they're extremely fast solvers, and I'll gradually discuss about ways by which we can develop algorithms which are largely motivated by the fast algorithms developed in the context of lasso. The theory is also very well understood. However, it has been reported in the literature, but there is one simple expression that I like to bring up, that is in terms of prediction accuracy. For example, there is a constant over here, 1 over gamma square, which is related to roughly speaking, how strongly correlated the covariates are. So in other words, if this gamma is small, this upper bound tends to be large. And in a sense, based on work that has been done, there are lower bound arguments as well, which essentially says that compared to this bound that you have, there are instances where the lasso is never going to attain this bound. Okay. Now, in order to fix this, statisticians have realized that this problem has to be fixed, and there have been several approaches as well, mainly based on non-convex regression. Now, non-convex regression methods are associated with algorithms. Now, if you use gradient descent kind of algorithms, they often lead to good solutions compared to L1 regularization. But as I will discuss, that these non-convex methods lead to complex optimization problems. And if you rethink the optimality properties associated with non-convex optimization, you see that you will get a hierarchy of solutions, and they lead to different solutions of different quality. I'll get to this after a few minutes. So the approach that we did was the notion of certifiably optimizing this, and the main workhorses were, as I said, we do not use only one particular area of optimization. We use techniques from discrete first order methods. These are essentially motivated by gradient descent methods, which are used in the context of first order methods and convex optimization. In the context of least squares, these have a special name. These are known as iterative Hart thresholding methods as well. But iterative Hart thresholding methods can be interpreted as gradient descent methods. And then if you interpret them as gradient descent methods, you can use many machinery over there from that area as well. So this is one class, and the other one, which was essentially exciting from my viewpoint, because I didn't really know the techniques in integer programming could be applied to solve statistics problems a few years back. And these are computational techniques from mixed integer optimization. So essentially, we take an engineering approach, put these things together, make something, and then hope that it is going to solve our problem. All right. In that context, it helped. And why should we be thinking about integer programming? This is because it's a matured subfield of mathematical optimization, and in the context of OR, or operations research, these are used a lot in various applications in the context of modeling and optimization for structured non-convex problems. Of course, these problems are NP hard, right? But what I like to stress over here is a problem being NP hard does not mean it cannot be solved. Okay, so there are several instances where an NP hard problem can be solved. Okay, so using computational techniques that are out there. For example, a classic example is the traveling salesman problem. There are several hardness results about the traveling salesman problem. But due to lots of research that has been done on this problem, you can solve the traveling salesman problem on your iPhone. Okay. So NP hardness is something that helps us understand how hard a problem is, but in practice, I think, even if a problem is NP hard, we should think about ways of approaching the problem using other machinery. Okay. And in particular, there have been significant improvements in software and algorithms in the last 10 years or so. So depending upon how you say it, I'd like to be very careful. So I'll quote one of my colleagues who is an integer programmer, and the way in which he quotes this speed up is, so if I look at algorithmic improvements, these are machine independent. I'm not talking about machines which are getting faster every year. Just algorithmic improvements. Simplex and Guruvi, these are two versions, commercial solvers, very high quality solvers. Every year, they undergo roughly a 2 times improvement in speed. All right, so and these are used in various applications. These are a bunch of companies which use these methods taken from Guru's website. The question is, okay, if you're giving a statistics problem which screams discrete structure, why can't we use it? At least play around with it. All right, so that has been the goal. So there are some examples of mixed integer optimization which are tractable in a sense. A lot of work has been done towards developing better solvers for this. One of these classes of mixed integer linear optimization problem. So mixed integer linear optimization problem is, it's a linear optimization problem where some of the variables are just binary. Okay. Mixed integer second order conic optimization problems are, it's a second order conic optimization problem. Most of the all the variables apart from some of the variables are continuous and some of the variables are binary. Okay, so if you give me a general problem which is non-convex like a neural net or very highly non-smooth continuous robust optimization problem, robust statistics problem for example, the chances are these techniques directly will not be applicable to them. Alright, because they may not be of the form of a mixed integer linear optimization, mixed integer second order conic optimization problem. But the chances are, if you think about the problem, massage it properly, you will be able to use these techniques to solve it. Okay? Alright, so flexibility. So let me write down the very basic version. This is the very basic formulation of the subset selection problem. I'll minimize the least squares loss. I have what is known as a big M. Beta i's are being controlled by big M times Zi. Zi is the binary variables. If Zi is 0, then beta I is going to be 0. If Zi is 1, then beta i's are going to be bounded by M. Alright, so this is a exact reformulation of the subset selection problem. This is the simplest version. The chances are, if you use this with a reasonable value of M, you will be able to solve this problem for that number of variables of the order of few hundred. Alright, but you can do better. Alright, anyway. Let's try to understand why I like this framework, why I find this framework appealing. That is because this is a real data set, diabetes. P is around 60 or 70, and N is around a few hundred. You let the algorithm run. Along the x-axis, you have the runtime of the algorithm. The upper bounds, that is the objective value, it goes down and then saturates. It has obtained the global minimum after a few seconds. But you don't really know whether you have obtained the global minimum. For that, you need lower bounds. All right? And these methods, just because they are the way in which they work, they do a branch and bound or a branch and cut strategy, where along time they give you a certificate of optimality by lower bounds. Okay? Now you may be thinking, all right, so for very large problems, these lower bounds are going to be bad. Yeah, fine, they will be bad. So what? Still then, I can define notions of local optimality. And then again, notions of local optimality for arbitrary non-convex quadratic problems are known to be NP-hard. But you can still say that, okay, I have a solution, and I know that there cannot be a solution, better solution in its neighborhood. Okay, so that's how I'll massage these problems to help me make better certificates about the problem that I'm thinking of. Flexibility. This is a particular example that I like. So I was giving a talk at the US Census Bureau. And after the talk, a researcher, Dr. Slutsky, he asked me that statisticians don't believe the models that they write in an applied problem. Okay, so I mean, chances are, if I want to find out the best model of size 6 on a regression problem, my model is wrong. So is there a way I can get a candidate of solutions instead of the best model of size 6? Okay. Now this is a case where it's a classic example of operations research. I mean, if you're thinking about ranking candidates in a committee, you're never going to come up with one particular candidate. Usually you come up with multiple candidates. Okay, so how do we do this in a disciplined fashion? Or in disciplined fashion using techniques in OR. So you don't have to think very hard about the techniques.
Rahul, can I ask
Yes.
a question? So not just what you're talking about, but let's suppose that instead of having one capital M, I had an MI, one for each
Yes.
variable. Could I take advantage of?
Yes, absolutely. You can. And that's so there are two. That's a very good point. So yes, you can take advantage of that. So if you have a priori knowledge about these MIs, you can encode that information over here. So if you think that based on a past study, I know that these amplitudes betas are going to be large, but these amplitudes are going to be small. These betas, you can encode that information. So that I would say is an instance where your statistical model building tools can be transferred over here, or statistical model building insights can be transferred into this object. There is another case where you can use data-driven MIs, then that is purely computational. So in a particular problem, some of the MIs are going to be large, some of the MIs are going to be small. So can you estimate that, learn that from the optimization problem? So these are two ways in which you can use it.
I also have a question. In terms of your lower bounds, is there any theory on how that curve became?
That's a very good question. No, and this is the place, as Boyd paraphrases it, this is the place where the NP hardness comes in. So there can be instances where you get solutions very fast, but certifying that you have obtained the solution can be very slow. Right, and as a matter of fact, so if you take these instances, solve observation problems, if you take the pairwise correlations to be very, very high, n to be small, p to be large, I'm messing up with the problem. These are cases where the lower bounds are going to be very bad. They're going to evolve very slowly. That doesn't mean they cannot be solved, you need more structure. And to an extent, Guru P doesn't understand this structure because it's very general purpose. So there's a lot to do over here. And in some cases, remarkably, these lower bounds you get very fast lower bounds. So a lot of this is not well known.
Are the algorithms randomized in any way, or are they?
So some aspects of this are randomized. So for example, if you use some of these simplex methods, at times they use a randomization technique to get over this degeneracy. But these are, apart from that, there is no randomization as such. And to answer the other, another way to think about the lower bounds is, see, the last one is going to give you a lower bound at stage 1. So that's the basic version of the lower bound. And then you throw in cuts or branch and bounded variables to improve it.
Is it possible to get a lower bound from your field of optimization?
Sorry, what?
The field optimization.
Yes, exactly. So these lower bounds are essentially done by optimization.
Oh, I see.
So what this tells you is that, okay, I'm minimizing this non-convex problem. You give me a subset. That's going to be give me an upper bound, right? But then how do I know how far am I from the solution? So that's where these lower bounds are.
I think she was asking if it came from a dual.
No. So it doesn't come from a dual. So these are known as dual bounds. But so this essentially these bounds essentially come from the relaxations. So think about solving an LP. What variable should I choose? X. Alright, so you have an AX less than equals to B, and then you have X binary. Suppose there are 10 variables. Okay, so this is a problem. Now I relax this. The basic way to get this is I relax this by saying that X is in between 0 and 1. So if I solve this problem by changing this into this, then I get a lower bound. Okay, that's a basic lower bound. And the way in which branching and bounding works is it says that, okay, I'm talking about a very basic version of this. It says that, all right, so I solve this problem, I see that the solutions are non-integral. So I know, suppose x1 turns out to be 0.6. x1 cannot be 0.6, it has to be either 0 or 1. So you fix it to be 0 or 1, and then you start branching. Okay, so that's one way to do this. Or in other words, you can throw in more additional constraints, and then that's how you get it. So that's essentially all the work is being done over here. Okay. Okay, so flexibility, computation. Okay, so let me skip this. So there are other ways by which you can improve this. So for example, you can get a bunch of bounds. This is related to the point that Richard was talking about. That you can, instead of having an elementary norm of beta less than equals to delta 1, 1, you can have element-wise bounds to be less than equals to different quantities. And these two problems are equivalent. If you just throw this side information in, then the chances are you'll get better low dual bounds. And then after one of the good things over here is there are some people in the integer programming community who are thinking about developing faster solvers for this class of methods. As a matter of fact, you can use some of these techniques, and essentially what that does is the epigraph of this is a ellipsoid. So you do a outer approximation to this, polyhedral outer approximation to this. And then if you refine these polyhedral approximations, then you can often solve these problems in shorter runs. All right, so the long story short, there are ways by which you can improve these methods. And many of these methods are directly driven by techniques that have been created in the integer programming already. Okay, let's summarize. What did we learn from this framework? So in summary, I'm not presenting numerical results here because I'll go over them in the context of the other project that I'll talk about. When the signal to noise ratio is high, so previously when I used to give this talk, I didn't write signal to noise ratio high, but now I make it a point that I say high SNR. So best subsets actually leads to very compact models, good prediction accuracy, good variable selection. And one place where, for example, methods like the lasso really suffer are in the context of compact models. In terms of prediction accuracy, lasso is usually good, but there can be cases where the lasso's prediction accuracy is going to suffer. And variable selection properties as well as compact models, this is a place where subset selection really shines. Let's talk about computational scalability. So if you think about y equals to x, the finding of the best linear model, you do not know what the k is. You want to tune k based on whatever, a separate validation set. The best size of k that you get is probably going to correspond to a model with size 10 non-zeros. Now if you use lasso to find out the optimal tuning parameter, it's probably going to correspond to a model of size 100. Okay, so that's usually the model size. Okay, I mean it happens because of the shrinkage part. All right, so the approach that I outlined, it can be slow in some cases. So usually it can take any time between 5 to 15 minutes or even longer to get a good solution. The certificates of optimality can be longer. Okay, it may be more time, it may take more time to get the good optimality certificates. There are some outstanding issues which are going to lead to the other talks that I talk about, to the other topics that I'll talk about. What actually happens if the signal is low? Is best subsets going to work? Is best subsets going to fail? If it fails, how badly is it going to fail? So on and so forth. And the other context is, if you're thinking about a daily data analysis problem, you have downloaded a data set and you want to play around with the data set to see some characteristics of it. Will you really be spending 5 to 10 minutes to get a good solution? Or do you want something which is rough and approximate to get a fast solution? Okay. Now, depending upon the people that I talk to, some people are okay in solving problems with number of features around hundreds and letting it run for overnight on different values of k, because the data sets that they analyze are probably to millions to generate data. They really want very sophisticated algorithms. But in some cases, if you want a very fast algorithm to understand what is going on, speed can be important. All right. All right. So in order to answer the first one, let's think about the question: is best subsets the holy grail? Right. So we say that best subsets is probably the best thing to solve if we had infinite computational resources. So I discussed in the previous part that okay, we do not have infinite computational resources, but still we can think about approximating solutions to this, to sizable problems, but is it the best? So let's think about a case. What is the signal to noise ratio? So Hasty, Tipshirani and Tipshirani, they uploaded a paper in arXiv around in 2007. They discussed the various findings of our paper, various aspects of best subset selection. And then, in one of the points that they mentioned, it's a very interesting aspect. I mean, I knew of this as a folklore when I was a graduate student. But then, most of the analysis or the experiments that were done were mainly in the small sample range, small p regime. But then if you start playing around with this, we see that if the signal to noise ratio is low, by the way, what do we mean by signal to noise ratio? Y equals to x beta plus error. I assume the data is generated by something of this form. and I'm just looking at the variance of this divided by the variance of this. All right, so high signal to noise ratio means sufficient signal, and low means otherwise. All right, so now we have been thinking about the low signal regime, and then we say that, all right, so if the case is low signal to noise ratio, I mean, the fact that substitution doesn't work, I mean, shouldn't really come as a surprise. Just look at the Gaussian sequence model. So if you look at the Gaussian sequence model, yi equals to mu I plus epsilon. Mu i's are given, you want to estimate mu i's and then have a certain amplitude, and then the epsilons are noise. Right, you start taking the value of the noise to be larger than the value of the signal. There's no way you can recover what these mu i's are. Okay, so it's not surprising that the subset solution doesn't work. As a matter of fact, the subset solution is a very simple case, boils down to d squares. And we know that if the noise is large, then we need to shrink. Okay, so what is the signal to noise ratio? Let me give you an example. So this is a case where we generate data y equals to x beta 0 plus epsilon, x is multivariate Gaussian, sigma is 0.8 to the power I minus j, the AR model. Beta is a binary, 0 and 1. The number of non-zeros in beta is 7. Let's take the signal to noise ratio to be equals to 1. N equals to 50, P equals to 200. Let's throw in our candidates out here. The prediction accuracy, prediction error, large means bad, small means good, and the number of non-zeros corresponding to the best model. So the candidates that I have over here are L0, subset selection. See, prediction accuracy wise is miserable. Let's look at the number of non-zeros. The number of non-zeros is low. This guy is 7. Okay, so 7, in this regime, nothing is going to happen. It's not going to recover the signals. Okay, because of this rule.
How do you choose the number of subsets?
So there is a separate validation set. On this, I train different models for different values of k, and I find out the value of k which minimizes the prediction accuracy on the validation set. Okay, so what L0 wants to do is, it wants to get a model with the best validation error, smallest validation error, and it realizes that it is overfitting. So in order to fight overfitting, it chooses a model with very, very low support size. Okay, so that's why this happens. Let's look at lasso. Lasso prediction accuracy is very good. Beats L0 because of shrinkage. Now let's look at L2. L2 is one of the algorithms out there. The L2 is just ridge regression. L2 is actually what's extremely well in terms of prediction accuracy. So I talk with my industry collaborators, the main thing that they use is L2. Because it just works very good in terms of prediction accuracy. They probably work with very high low signal to noise ratio as well. Prediction accuracy of L2 is pretty good, but now let's think about the number of non-zeros. L2 is of course going to be dense. L1 is out here. L1 is P is a polished version of the lasso. It has fewer non-zeros. But again, L1 polish also suffers in terms of prediction accuracy. Okay, so this is the behavior. All right. Now, so how do we fix this? So what we thought is a very, very simple solution. Okay, I think there is something very deep going on over here. I completely don't understand. There may be ways to analyze, to understand this by using Bayesian ideas like model averaging and things like that. But we are still exploring. We do not have a complete solution to this. But this is one proposal approach. So what we do is, all right, so lasso or L2 is doing well because it imparts shrinkage. L0 selects. So let's think of putting both these things together. All right. Now, the way in which I like to think about this problem is as follows. I mean, this object is this estimator is used always in recommender systems, in low light analysis. So if you're familiar with that area, you'll see that one of the best algorithms to reach good predictive accuracy is a one which does a regularized singular value decomposition, which essentially does a ridge regularization on the L2 factors of the latent on the latent factors, and also does a rank minimization, which roughly in the singular space is going to correspond to an L1 regularized. It's going to be an L1 stemming from the L1 nuclear norm. This is going to be the rank. Okay, and it has been used with a great deal of success in recommender system applications. Now, of course, that is in the spectral space, but this is in the vector space. In vectors. So let's see how this works. So this is L0 plus L1 and this is L0 plus L2. You see, if you think about prediction accuracy, now you start comparing versus, get methods comparable to L1 as well as L2. Now, if you look at the number of non-zeros, an interesting thing happens. So these guys, of course, now start to be dense. They're going to be more dense than L0, but they are going to be much sparser than L1. Okay, and this is a phenomenon that we actually see in this class of problems. So if I look at this object and think about studying what properties it may have, if the signal strength is very large, then this guy is going to get the benefits of subtle selection, right? Because lasso high signal to noise ratio, its prediction accuracy may suffer, especially in terms of correlations. But if you're talking about a low signal to noise ratio, low signal, then this guy is going to be a mess. I mean, unregularizing is not going to be, unregularized estimator is going to be very bad. You need to shrink. But on top of that, what this guy can do is, it's going to further sparsify. So the L1 may choose a model which is very dense. Sorry, now density is over here. And these guys are going to further sparsify. Okay, and you have a joint optimization criteria explaining how to go about one way of approaching the problem.
I mean, it's
Yes.
pretty similar to the elastic net. What's going on.
Yes, it is. It is similar to the elastic net. It is similar to the adaptive elastic net. It is also similar to the L2 regularized MC plus penalty. Actually, that's very interesting. So I actually spoke about this with Kulhui. And then if you look at these papers over there, one of the emphasis seems to be, all right, so I have X's which are correlated. I want to do a better job in terms of estimating my beta, my underlying regression coefficient. Can I solve a problem of this form with L2 with a non-convex penalty, do a better job in estimation? The signal to noise ratio is going to be high. But over here, this is a regime where the signal is low. And this is a regime, by the way, where you can show the variable selection does not make sense. It's going to be completely catastrophic. So when we make any statements about this problem, we say that, okay, this is a regime where we cannot make any statements about variable selection at all, about correct variable selection. The only two things that we can talk about are prediction error and how dense your model is, or how many non-zeros you have. Okay, so yes.
Your prediction error also contains the lambda, the regularizer part.
Yes, yes. So lambda essentially,
It's from cross
if you do validation, yes. So essentially, it's going to detect based on the amount of noise that it has, whether it has to shrink hard or not.
So if we only care about prediction error and not actually correct variable selection, why
So
do we
these are-
want a sparse model?
Sorry, say that
I
again.
mean, so if you're saying that we're not doing correct variable selection, so
Mhm.
maybe there were 7 non-zeros and we're picking 7, but they're completely wrong.
They might be, yeah. that
Right,
can
so
happen.
why do we even care about it being sparse then?
Okay, so because one of the main reasons why sparsity is used is from a practical context is because it leads to a compact model. So if you think about predictions in an industry context, right? If you have a model, I want to do very fast predictions. Then if my model has like 20,000 non-zeros, it's going to be difficult for me to do real-time prediction. If I have a much sparser model with fewer non-zeros, it's going to be easier for me to load, to store, that's one. And the other thing that people say is the interpretability story, which I also think is important. Like for example, in many neuroscience applications where you have you have the two models with very similar prediction accuracy. One of them is much sparser than the other one. I'm talking about L1 versus L2. In those cases, the L1 story goes as follows. I have a model which is much sparser than the other. It makes sense to me, it's more interpretable. So I want a model which is more sparse. Now but you're right, I mean, in fact, there is a result by Gamanik and Zadik who say that, okay, if in a binary sequence model, if beta is a binary, if xi is ideally Gaussian, then the number of samples that you need for perfect recovery is going to be, there is a threshold, n is larger than n star, then you will be able to do variable selection, otherwise it's going to be catastrophic. And the n star that you need for the lasso is going to be much larger. So variable selection, I mean, see, so variable selection doesn't make sense. And honestly, in these cases, this is the thing, again, that I've seen based on playing around with these problems, if n is 50, p is 5,000 or 10,000, there is a lot of noise, lots of correlation. Even if you generate data from an ID Gaussian, you cannot recover that signal correctly. So true variable selection doesn't make sense in these problems. But still, I think, I mean, it's good to have an understanding about, I mean, if in this SNR, if this is how my data behaves, then variable selection can be done with this amount of data. But in real problems, we don't even know whether there's an underlying ground truth in our work. Okay.
Is there also a regime for like below which even the prediction error tends to be a bit noisy?
It can be. So okay. So I'll talk about that. I'll answer that based on numerics. Okay. So I'll hopefully have time to do this. Okay. So now let's so essentially, okay. So now let's talk about faster surface selection. Now the other part over here that I'd like to say is, as I said, compared to algorithms for lasso or non-convex algorithms, which are much faster. These methods that I propose, these are based on mathematical optimization routines. They do their job. They are interested in getting lower bounds, very advanced routines. So they do not exploit problem structure as much as you would like it to use. So how can we solve larger problems? So this is something that we have been working on over the past couple of years. We just uploaded it on archive if you're interested. So it's on fast-based surface selection, and then the title says it's based on coordinate descent, which is one of the main workhorses for convex optimization problems, and it has an additional twist, which we have seen seems to lead to a big gain in practice. There is a notion of combinatorial optimization. So it does local coordinate descent, and as I'll argue, coordinate descent may get stuck in very bad solutions, depending upon the difficulty of the problem level. But you can do better if you use more advanced search heuristics. So this is joint work with my student Hussein, who is a student at the ORC. So, so the question is, can we bridge the gap between the speed, can we have an algorithm which is nearly as fast as a lasso, and in terms of metrics, variable selection property metrics, and things like that, can it have properties which are similar to best subsets? There has been a lot of work that has been going on in coordinate descent, I'd like to mention, but the work that we have been doing extends a notion which was implicit in a paper written by Beck and Elder in 2012, and Beck wrote a few follow-up papers on this. These are all papers in the optimization journal. So there was a notion that was implicit. We took that notion and thought about using it in this particular context. So what it uses is, the main idea is as follows. If you want to solve a problem where P is of the order of 1 million, N is of the order of 500, global optimization based methods are going to be too ambitious. I mean, at the moment it's going to be ambitious. What will I do for those problems? Can I have a method which scales as fast as a lasso? But can the properties be very similar to L0 type problems? Okay, so that's the goal. So in order to do that, we consider this class of problems. Why do I throw this in? Because of the low SNR, low signal to noise ratio story. Because if you throw these guys in, then it's going to do a right trade-off between high signal, low signal, as well as this guy is going to do surface selection. We are doing the Lagrangian version because the Lagrangian version helps us to do the algorithms. This guy is a data fidelity, this is a shrinkage, and this is a sparsity. And of course, we do not deal with 3 tuning parameters, we deal with 2 tuning parameters. Consider the cases this, and this. And then, this is at the heart of the idea. We describe the notions of necessary optimal conditions. So we take a solution beta star. If it has to be a global solution, then it has to satisfy some necessary optimality conditions. And that leads to a hierarchy of optimality conditions. And this hierarchy can be directly transferred to algorithms. Okay? Yes?
If you've got these additional L0 and L1 constraints, is there a particular advantage to having the square of the L2 norm feature rather than just the ordinary L2 norm feature?
So square of the L2 norm I had over here mainly because it helps in algorithm computation.
It helps.
Yeah, that's it. But if you solve this problem for a sequence of lambda 2 values, family of lambda 2 values, then you can map the L2 square to the other one.
Like a kind of square
Right.
class.
I have a related question. If you solved your earlier problem where you have the L0 constraint in either an L1 norm or an L2 norm, is that going to be a problem with your mixed integer
Yeah.
optimization?
Yes, so this problem that you have, this can be written as an instance of mixed integer second order quantum. That's why you took u to be equals to 1, 2, not 1.5. I cannot do 1.5. Actually, 1.5 can still be written as MISOC, but yeah, 1 or 2. But again, this inherits the scalability properties roughly as of a solution that I got. Okay, so we consider these cases necessary optimality conditions, and that is going to lead to a hierarchy of optimality or stationarity conditions. It is a package we pushed. Who said to do this? And it did in R, by the way. The previous guys were all in Julia. I don't know. We at MIT are crazy about Julia. It's fast as C and it is as easy as MATLAB. But statisticians love to use R. And if you want to play around with this, I'd be happy if you play around with this and give us comments. So it actually implements all these algorithms, all these methods, and it's actually pretty easy to call these methods. So let's give you a glimpse of the timing results. And now, there has been a lot of work that has gone into this to get at a scale which is comparable to the lasso, for example. This is GlimNet, this is NCVReg, this is another algorithm which is based on MC plus regularized non-convex regression. These are the timings. This is a problem with P equals to 180,000, N equals to 250,000, 2,500. So you see, so timing wise, GlimNet is 50 seconds, this L0 learn is 30 seconds. The point is, I'm not highlighting over here that 30 seconds and 50 seconds is a big difference. That's not the case. But what I'm saying is, all right, so if you really want to do a real data analysis problem, why will you use a nuclear weapon like integer programming? You'll use something simple, which scales effortlessly to very large scale problems, and these are candidates for it. Okay?
Rahul,
Yes.
the same training parameter sequence to compare different methods.
Right. Yeah. So this is then based on a validation set.
Okay, so they,
Yeah.
they all have the same candidates.
Correct. Now the main difference is in terms of MSE. All right. So GlimNet is actually the best in terms of MSE. But let's look at the number of non-zeros. This is a big game, and this is a real data set. I mean, probably if you generate synthetic values of beta based on this, you're never going to recover the regression coefficients on this, right? But the number of non-zeros that you get is much smaller. All right, and this is another data set with a similar story. All right, so now let's go over the optimality conditions for this class of problems. One of the classic notions of optimality for this is the notion of stationary conditions. That is as follows: you give me a support, you give me a subset S of P, I can do a lower dimensional optimization problem and then solve and get a solution. All right, this guy is the convex part, so I can solve it. That is going to give me a notion of a stationary condition. There is a notion of optimality conditions which is inspired by iterative Hart thresholding. Now, this is interesting. IHT is considered to be one of the best algorithms out there for cardinality constraint regression. And if you study the stationarity conditions, IHT is very bad. In fact, IHT can be beaten by coordinate research. An algorithm which is as simple as Gauss-Seidel applied to this problem. If you define stationarity conditions corresponding to this, you can show that this is a much smaller class than this. And this has to do with the choice of a Lipschitz, with the choice of L. For IHT to converge, you have to take L to be large enough, which means this to be a smaller class than this, and this is a smaller class to this. In fact, you can do better. And this is a place where computational optimization comes in, and this turns out to be key in difficult instances. The notion of, this is Hussein's name, by the way. I mean, he said swap inescapable minima. It's difficult to pronounce, but anyway. So let S be the support of a beta star. The partial swap inescapable minima, what that essentially does is, it takes your beta star, it looks at the support of beta star. It starts removing elements from the support of S star, and then starts adding elements to outside the support of S. Right? So I have a solution. I want to perturb the solution. So what I do is, I look at the current solution, I start removing some entries from it, and then I start adding non-zero entries to outside the support. All right? So this is the notion of a swap, and I do this to improve my solution. Okay? So this is the notion of a partial swap, and you can also define a notion of a full swap, and essentially they differ in the way in which they optimize after changing the coordinates, after changing the support.
What is U?
What is what?
U.
So U is an operator which essentially takes beta star and then looks at the entries restricted to S1. Okay. So probably, so the notations look clumsy, but I'll give a picture which is going to help illustrate the idea. So this gives you the hierarchy. So the largest one is the stationary minima, then IHT, then coordinate wise minimum, partial swap, full swap, and these can be defined of the order k. If k becomes larger, then you start colliding, becoming the same with the set of optimal solutions to the problem. But of course, if you want to solve very large scale problems, you cannot take k to be large. You have to take k to be 1 or 2. If you're solving 1 million size problems, k can be 1 or 2, few seconds. Okay. All right, and this is the place where local combinatorial optimization comes in, and I'll show. I mean, this actually leads to a big improvement, especially when the problem becomes difficult. This actually leads to a big improvement. And all these notions. So we started with the class of problems. We talked about stationarity conditions, and all these stationary conditions naturally lead to algorithms. Okay, so let me illustrate one algorithm by a picture. So talking about the partial swap idea. So I have a solution with me based on coordinate descent. This, sorry?
The cigarette?
Oh, yeah, it looks like so. So, and this is the support, S, and this is S complement. Now what I do is, I take to these two entries from S, and I throw in a few other guys from S complement. And so these guys which were initially in the support, I'll send them to be non-support point indices. These guys which are outside the support, I'll make them to be support indices. I'll do an optimization over here. And once I get an optimization, I get a new solution. This is a swap. And then I apply coordinate descent, and this is how the algorithm works. Okay, so it looks complicated in notation, but it's actually very simple. All right, so special case swaps of order 1. If you do a careful implementation, then you can reduce the cost of the problem. Partial swaps, as you may have imagined, this can be written directly as an integer programming problem. So it depends upon this is the hierarchy says that depending upon the amount of time that you have, you can take k to be larger, and you can see how these problems solve over time. Now let's try to understand the statistical performance. And with these types of algorithms, just because they are very fast, we can just run them on the server and get solutions very easily. All right, so this is a case where X is IID Gaussian. Sorry, X is the data matrix X is drawn from a multivariate Gaussian. When I say exponential correlation, I mean sigma ij. The pairwise correlations are of the order 0.9 to the power absolute I minus j. Okay, this is a hard instance. You need to take hard instances to see differences. All right, P is 1000. N, the number of samples you start getting. Okay, this is the probability of full recovery. So essentially, this is the strongest possible notion. So you make any one mistake, the error is going to be, the metric is going to be 0. All right. So probability 1 means all the guys have been selected, all the non-zero, the whole support has been recovered. Okay. So now let's see. So this is the L0, L2 swaps. This is the L0 and L2 with the swaps, 100 swaps. You look at the number of samples, you see the probability of full recovery. There is a phase transition that happens at a much smaller value of n. Now let's see L0. This is just coordinate descent applied to L0. Coordinate descent applied to L0, the algorithm is weak. The stationary conditions are also weak. Look at the quality of solutions. I mean, you see the effect, right? I mean, it doesn't get the actual underlying solution. The algorithm also has implications in the context of the solution it recovers. Now let's see L1. L1 is 0. L1 relaxed is a version that was proposed by Hastings Shirani as to say that okay, it does better than L1 on a wide array of regimes. L1 relaxed has the same variable selection properties as L1. It is all 0. This is your MC plus. Where is MC plus? So MC plus is also over here. Forward stepwise is over here. Okay, so you see the heuristic. So there is a clear separation. Heuristics, and these are advanced heuristics. Everything is a heuristic, but one of them uses local combinatorial optimization. The other one does not use it. This is probability of full recovery. Let's look at prediction accuracy. Even in terms of prediction accuracy, you do see that there is a difference. This one seems to be the best. This is the L1. L1 relaxed does slightly better, and which is a forward stepwise is over here. So you see when the number of samples is sufficiently large, then all the methods start behaving similarly, which is expected. You want to see differences, then you have to go to these regimes. Any small, very high correlations. Let's look at the support size. The support size also a similar story. That is the number of samples. Usually the L0 methods lead to much smaller support sizes. Stepwise is also pretty good in terms of support size. But we saw the full story regarding the variable selection properties. So it's going to be reflected over here. Now let's look at an example where we decrease the level of correlation. So the previous one was 0.9 to the power I minus j. This is a case of mild correlation. You see in the case of mild correlation, there is no much difference between L0 and L0L2. So advanced combinatorial optimization and simple heuristics like coordinate descent, they perform similarly. Okay, so you see there is a hierarchy in the optimality conditions for a problem, and that is directly related to the hierarchy in the quality of solutions obtained. So the problem is harder, then you really need to do a hard optimization. If the problem is easier, then simple methods are going to work as well. Okay?
What happened to MCP?
I don't know. So MCP is in spirit similar to just coordinate descent, right? It doesn't use the swaps idea. So that makes it, that actually gives it a big boost. Okay, yeah, and also we are using just existing software for MCP. We do not take no responsibility for optimizing MCP. I couldn't convince Hussein to look at MCP. Looking at, okay. All right, so now let's look at a case where we are varying signal noise ratio. N is fixed at 1000, P is 5000, rho is 0.5, and this is a case of constant correlation. So all rho ij's are equals to rho. It's not exponential decay. All pairwise correlations are rho. All right, so as I said, if the signal to noise ratio is low, variable selection does not make sense. Over here, I mean, all methods have zero probability. Over here, you start seeing effects that L0, L2 may start picking up. Now, let's look at the support size. So there was a question about what is going to happen in the very low signal to noise ratio. In the very, very low signal to noise ratio, let's look at the prediction accuracy. L2 shines. L2 is the best in low signal to noise ratio. L1 is not that good in terms of variables, in terms of this prediction accuracy error, but a close by candidate is L0, L2, and that's because it's probably borrowing strength from the L2 part. Now you see what happens to the support size. See the signal to noise ratio, this is something that I don't understand very well. If the signal to noise ratio is low, in order to get the best predictive model, what L0, L2 tries to do is, it selects probably a bunch of candidate models and probably aggregates them in some fashion. Otherwise, how can I explain the fact that there are 50 non-zeros in a model, but the best model obtained by L0, L2 has a support size of around 250. So, this is something that we do not completely understand actually, why is this happening? But this is the hand way we are going to show, to get one. Yeah, I'm just thinking out loud. Okay, but this is what happens. Okay, Gaussian mixers. Can I take a few minutes or no?
We should probably wrap up.
Okay. Oh, should I do or no?
If you're okay with people leaving the room, you can keep going.
Okay, that's fine. So let me then, it's not good to go over time. All right, so let me just go to the conclusion. So statistical thinking, these are all cases. These are all gives rise to excellent estimators. And I mean, statisticians are usually extremely good at coming up with estimators. I mean, look at classical text, we will see estimators all around with fantastic properties. And mathematical optimization, at least this was one perspective that I presented. I start with the estimators as they are presented, and then we think about ways by which these estimators can be computed using several domains of computational mathematical optimization. And the eventual goal is to better understand estimators and then create new tools at the intersection of statistics and data science. Thank you.
Any last questions?
Do you think the SNR is the only issue that impacts the performance of the best subset selection?
Impact, okay, no, so no, there are many issues. So look, one of them is if you really want to see why best subset has an edge over the L1, you need to start playing around with the correlations, sample correlations.
Okay.
That's one place, all right? Now usually these are regimes that are well understood. If you can solve this problem optimally, then you get performance is better than L1. But implicit in this, in our understanding is that we assume the signal noise ratio is very high, all right? Now if you start playing around with best subset, which is just one estimator, right? You can break it. So in order to break it, if you play around with SNR, then you start breaking it. Okay, but again, in all these cases, we are assuming that there is an underlying sparse model, so on and so. So all the assumptions that are needed for with which we usually generate data. Let me put it this way: all the assumptions with which we generate data, underlying sparse model, correlations, blah blah blah. All these are there. But if you really want to break a subset selection, bring SNR to below. But then the fix that I proposed over here is, it's probably not a big deal. Just add a little bit of a shrinkage.
Have you thought about the sparse PCA problem? That would seem to
Yeah,
work
we
well.
had okay, a little bit, not much. Sparse PCA is a much harder problem. Much harder problem because you're maximizing a convex function subject to cardinality constraints. This is much harder. You cannot put it into a MIP format. There has been some work we did with Shantanu De, who is an integer programmer at Georgia Tech. So this is what we have. Okay, so we look at maximizing X transpose sigma X. Alright, so this is the usual version of the PCA. If you relax this guy to L1, the L1 version of sparse PCA, which is still hard because it's maximizing it's a non-convex optimization problem. This is more tractable. I mean, this at least you can solve two problems up to a few hundred variables. But you need to do this. And also there is reason to believe that, so also there is a result where we showed that if you do the relaxation over here, no matter what sigma is, you're always going to have a constant factor approximation to the actual L0 problem. So if you like this problem, which I think I like, it's not a bad problem, right? I mean, L1, you probably are not going to get as much sparsity as you want like L0, but this is this is a tractable problem. But few hundred is the best that you can do.
So before you don't really know if you apply this, that you will reach a solution, right? So do you have any idea how that affects the statistical analysis? Because then it's more or less conditional on that you have found a solution.
The statistical analysis, so the focus, there is one statistical analysis, which we didn't really get in a textbook. That is where we talked about the subset regularized problem. But that was, we said that, okay, so that's few hundred to thousands. Integer programming is going to solve the problem, and assuming that integer programming solves the problem, this is what the statistical properties are. So it's a global solution result. But for all the recent methods that I discussed, these we do not have any statistical properties for this. So all these methods, the algorithms that I proposed, all that I showed was empirical results. I have no idea about what the statistical properties of this is, or how, from a statistical viewpoint, you can show that coordinate descent with one swaps is going to lead to better solutions than iterative hard thresholding. Where is it going to come in? Probably not the rates, probably the constants. I have no idea.
They actually mean that you have a data set and it happens to be the one where you can't reach the solution. So that's whether or not you get a solution is a random event.
Right. So exactly. So in these problems, we have not, so correct. So in this case, so in all these examples that I discussed, there are these algorithms like L0, forward stepwise, L0, L2, and all these. These, we do not claim we are getting the global solution. It's an algorithm which reaches a stationary point suitably defined.
You always get some stationary.
Yes, and that's the place where this hierarchy comes in. So for example, yeah, so the largest class is stationary minima, and then if you do iterative hard thresholding, then you get over here. If you do coordinate-wise updates, you get over here. And partial swaps and full swap, you take a coordinate-wise minima, you start swapping them, and then you get a solution. I agree, this can depend upon the initialization. So this is correct. But all the but all the algorithms and the results that I presented, I'm making no claim about global optimality. All the optimality certificates that we have are the algorithm reaches these stationary classes. It may be a global minima, it may not be. And so the conjecture is okay. So in some instances which are easy, you can just you can use this and then verify with integer programming whether it has reached the global solution or not. So in many of the cases when we do get, say, so for example, perfect support recovery, like in these cases, perfect support recovery, we believe that this has obtained the global solution, but the algorithms, the way in which they are presented, or say, these algorithms are going to exit in a few seconds. When they exit in a few seconds, they're not going to tell you that I've reached the global minimum. But they will tell you the following.
Olin could probably tell you that they're all close to the truth.
I don't know about this particular objective.
Oh, that's possible. So actually, so yeah, so this is the thing. So one thing is, this is the thing that we do not understand very well. In terms of objective, it is probably reached very close, but there is a big price to pay in terms of support recovery. So you are very, very close to the solution, right? 10% off from the solution. You now start making changes. Supports start changing like wildly. Is that something that can be understood? I don't know actually. It would be good to understand this. I have no idea.
That sounds like a good topic.
Right, maybe let's thank Rahul again.